solve another Leetcode problem. 1514. Path with maximum probability. So for this problem, we are giving a graph, and we are also giving edges. And inside the edges, for example, this is a 0 to 1, and 0 to 1, it is bidirectionally connected. And we are also giving a success probability. So, for example, 0 to 1, the probability is 0.5. 1 to 2, the probability is 0.5. 0 to 2, the probability is 0.2. But we're going to return the maximum probability from the starting point to the ending point. So we are also giving the start and end. For example, here we are giving the start node and the end node. So for this example, from node 0 to node 2, we're going to return 0.25 because 0.5 times 0.5, it is the 0.25. That will be the maximum. Yeah. But here, from 0 to 2, the probability is only 0.2. It is not bigger than 0.25. So we're going to always return the maximum probability from starting point to the ending point. So this is a typical Dijkstra's shortest path problem. But for the shortest path, we're going to always check the minimum. But for this problem, we're going to calculate the maximum. So we need to do a little bit of trick. So in mathematics, if we want to calculate the maximum value, yeah, we're gonna use a negative value. So we're gonna calculate the smallest, the negative value. For example, minus 0 to 0.25. If it is the minus, if it is a negative 0.25, so it's gonna be the smallest value because negative 0.2 would be bigger than negative 0.25. So if we gonna use the Dijkstra's algorithm, we're gonna always calculate the smallest value. If we have a negative sign for each of the paths, so we're gonna calculate the shortest path. We can turn this problem into a shortest path problem. Yeah. Now let's just start coding. Yeah, I'm gonna prepare some preparations. I'm gonna prepare an adjacency list. It would be a default dict, and inside it's gonna be a list. Now I'm gonna enumerate because I will use the index because I'm gonna use the numbers inside the success probability. So for I, U, V, in enumerate the edges, what I'm gonna do, I'm gonna just prepare the adjacency list first. So GU should dot append inside and gonna be the node V and with a probability of I, but this I is the success probability I. And similarly, I'm gonna prepare the GV because it is bidirectionally connected. So I'm gonna put the U and the success probability gonna be I. So this is the preparation for the adjacency list. Now we're gonna start the Dijkstra's algorithm. So PQ is gonna be a tuple inside. So for the first value, as I said, I'm gonna prepare the negative path. So finally, from 0 to 2, it's gonna be the negative 0.25. Yeah. So inside, I'm gonna give a minus 1 because from the beginning, I will prepare from the starting point, from the starting node, from the beginning, I'm gonna prepare it as a negative 1, and the node will be just the starting point. So it will be negative 1 and the start node. Yeah. Now I'm going to prepare a list array. So inside, because I'm going to calculate the shortest path, the smallest value, so I'm going to have an infinite times the number of nodes. And the list start node will be minus 1. So this is the preparation. It is totally the same as the Dijkstra's algorithm, but for this problem, it is a probability problem. We need to prepare the negative 1 or positive 1. Because for this problem, I'm gonna use the Dijkstra's algorithm. I'm gonna use a negative 1 because the smallest value is our final result. If it is the smallest negative value, it means it is the biggest positive value. Yeah. So from the starting point, the start node, I will give a -1. And then, for example, the start node is 0, I will have a -1, and then it goes to node 1. Currently, I'm gonna have a minus 0.5, and when it goes to 2, it's gonna be minus 0.25. Yeah, but for 0.2, but from 0 to 2 directly, it will be negative 0.2. Yeah, but finally, inside the priority queue, I will pop out 0.25 first because this is the min heap. Yeah, it will always be the min heap, and inside the it will be a min heap, and it will have a tuple of the distance. Yeah, it will be the same. Here, it will be the probability, and with the starting node, it is the probability and the node. Yeah. Now I'm going to just use a while loop, check the priority queue. I'm gonna pop out the probability and the first node. Yeah, it will be the heap pop of the priority queue. Now I'm going to check its neighbors. So for the neighbor and its probability from the starting point to this current node, yeah, I will have a probability. Actually, it is this edge. Yeah, so it would be inside the G with this node. Now I'm going to calculate the cost. So the cost will be P times the probability. If the cost is smaller than the distance of the neighbor, so the distance of the neighbor will be updated with this cost. Now I'm going to put the tuple inside the priority queue. So the tuple inside first value will be the cost. Yeah, and the second value will be, yeah, the first one will be the cost, it is a probability. The second one will be the node. So the node currently, it will be the neighbor. If I didn't find the value, I'm gonna return 0. So it means the probability is 0. If I find it, I'm gonna check it. So if node equal to last node, or the add node, yeah, it is add node. So I'm gonna return this probability. But currently, this probability is a negative value. I need to return a positive value. So I need to return a minus p. That means the final result would be a positive value. Yeah, I think everything should be okay. Now let me just run it to check if it works. So here, it is a default dict. There is a typo. Yeah, as you can see, it works. Yeah. Now let me just submit it. After that, I'm gonna analyze the time complexity. Yeah, as you can see, it works and it's pretty fast. So the time complexity is just E log V. E is the number of edges, V is the number of nodes. Let's just check. The number of edges, how many number of edges? It would be 2 times 10 to the power of 4. And how many vertices? It's gonna be n, 10 to the power of 4. Yeah, basically the time complexity is n log n because this is a sparse graph. It is not a dense graph. Yeah, basically it is n log n. Thank you for watching. See you next time.